Hi all, we're going to go over a very short section on Achieve today with section 1.3. Probably won't take you much time at all. Let me go ahead and share with you what I've done with this section here. I'll pull up my screen and here we go. First question. This one's talking about just finding the domain of a very simplistic function, and I'll go ahead and show my worksheet here too. This function g of t, which is equal to t to the 7/3, you just need to remember, well, that's the cube root of t to the 7th. What are you supposed to know about every cube root function in existence? Well, all odd roots, not just cube roots, have an infinite domain. So t can be any real number. In interval notation, I'd say negative infinity to infinity. They want the wimpier all real numbers answer for here. So that was my first one. Moving on to the second question. Again, it's just concerned about the domain of this function. That's all we're doing. And you should automatically look at it and say, it's a rational function. What do we know about all rational functions? Well, they have vertical asymptotes or are otherwise undefined whenever the denominator is 0. So all I have to do is set the denominator equal to 0 and say that function's not existing at that value. In this case, t plus 2 cannot equal 0, thus t cannot equal -2. And you see I put t equals -2 for the solution. The third one here, it's a bit trickier. Again, it's asking us to find the domain, but you've got to be careful. You can say, okay, yes, it's a rational function, so any terms that are in the denominator of that rational function cannot be allowed to be 0. That's true. But also, please notice you have a rational function within the numerator, because x to the -3 is the same thing as 1 over x cubed. And so you'd say, well, I know that the denominator of that term can't be 0 either, so I know x cubed cannot be 0. The x plus 18 cannot be 0, and the x minus 6 cannot be 0. And so now I would have actually preferred the gorgeous interval notation from negative infinity to -18 union -18 to 0 union 0 to 6 union 6 to infinity. That would have been a beautiful answer. But no, they're sticking with this all real numbers, and they use the script R in this case, so I did too here on my work. And so you could say it's all real numbers except these 3 restricted values, and they will want you to put the restricted values in order. So except x equals -18, 0, and 6. And mine, it was the second to last option for the solution. Up next, it's looking at composition of functions. The 2 functions it gave me in this problem was f of x is 1 over x, and g of x is x to the -6th, which I know is 1 over x to the 6th. So here, first thing I did is I went ahead and found the composition. It said find f composed with g. Now, I went ahead and wrote the f composed with g as f of g of x. That's what f composed with g means. So we're going to take g of x, put it into the place of x within f of x. Well, g, that's pretty easy in this case, because if you put that g of x into the place of x with an f of x, you just get 1 over x to the -6th. And then you know, anytime you have a negative term, a term to the negative power in the denominator, that term belongs in the numerator to the positive power. So this is simplified to be x to the 6th. Now, when it's asking the domain of f composed with g, what you should be concerning yourself with is, okay, in order for that function to exist, the inside function must exist. Well, g of x only exists if x cannot equal 0, and that's the same for f of x in this problem too, because this is the same thing as 1 over x to the 6th, and I know 1 over x to the 6th does not exist if x is 0. So when I'm looking at this, and now the mistake students will make in this is they'll look at their answer and say, well, that answer exists everywhere. Well, yeah, it does, but that answer can't exist if the original function couldn't exist in the first place. And if g of x cannot exist, then f could never been composed with g of x. So you still have that domain restriction at 0, despite your answer being a nice polynomial. So notice here, when I answered that part out, I get the f composed with g is x cubed. The domain of f composed with g is all real numbers except 0. And fortunately, it does want an interval notation here. So from negative infinity to 0, union 0 to infinity. Now, oddly enough, usually f composed with g and g composed with f give you different answers. Not in this problem. Then they ask you to find g composed with f. So g of f of x. You're taking the term in f of x, plugging it into the place of x within g of x. So we're going to get the group 1 over x raised to the negative 6. You say, well, if I have a group raised to the negative 6, then I can just get rid of the negative by taking the reciprocal of what's on the inside, because that negative is telling me everything is belonging in the wrong place in the fraction. So I can say, well, then this is just the same thing as x to the 6th, which is the same thing as the other direction of the composition. Pretty cool. Now, again, you would say, well, g of f of x could only exist if f of x existed in the first place. F of x has a domain restriction of 0, so my composition still has to have a domain restriction of 0, despite the fact that the composed function is a nice polynomial. And yet again, you'll see I have the g of f of x and the domain down there. Nice problem. For number 5, again, composition, but the composition's a little more fun, and it could throw you off because usually when people are working with compositions, they're accustomed to having the same variable in both functions. That's not necessarily always has to be true. About 99% of the time, it's what we see, but it's no big deal. In this case, if I have f given in terms of theta, and it's equal to the cosine of theta, g is in terms of x, and it's equal to 5x squared plus 8x. Please notice the first thing they asked me is to find f composed with g of x. Well, all right, and how did I already know it'd be f of g of x? Well, because if your inside function is going to be your g function, we know g is in terms of x. So it's telling you, take the function g of x, replace it for the independent variable within f. You can say, well, the independent variable in f is theta. So instead of f of theta, it's f of g of x. So I say 5x squared plus 8x, take the place of theta within f of theta, and I just get f of g of x is equal to the cosine of 5x squared plus 8x. And then when I'm thinking about the domain of that composition, I'd say, well, all right, the domain is going to be restricted by the inside function that you're plugging in, but the inside function g of x is a polynomial function, okay? And it's also restricted by whatever function you get. Well, it's the cosine. Cosine functions exist everywhere either. They're never restricted for any angle. So automatically I know that f of g of x is the cosine of 5x squared plus 8x, and it has a domain from negative infinity to infinity. You can see that's what I put there for the first two. Now, I could see some students running into a little bit more problem with this second one here. If I ask you g of f of theta, all right, you're saying, well, let's just take the function f of theta, substitute it everywhere we see the independent variable x within g of x. So instead of g of x, we have g of f of theta. That's going to become 5 of the cosine of theta, quantity squared, plus 8 times the cosine of theta. Now, you can either leave it like I have here, or most people would write that as 5 cosine squared theta and put the squared right after the cosine, but this is fine. And yet again, you would look at it and say it has an infinite domain. Now, the domain this time has to be in terms of theta, since that's our variable in the problem. And you can say, well, we know that the cosine of theta always exists for any value of theta. Therefore, this has an infinite domain. Theta equals negative infinity to infinity. And you can see that's where I put the remainder of the values there. Now, last problem in this section. Take a look at it here. Oh, and this was having you graph a piecewise function. And the piecewise function they gave, or at least me, on this one, it was a rather boring piecewise function. It's only a two-part piecewise function. It's saying, let's let f of x equal 9 for all x values less than 0. So I went ahead and just drew a constant function, y equals 9, for all x values less than 0. Now, if I were just drawing that, I would have put an open circle on the ordered pair 0, -9. Why is there a solid dot there? Well, because notice where your second function picked up. F of x is equal to the quadratic x squared plus 9 for all x values greater than or equal to 0. So I could say, well, all right, when x is 0, this y value is still 9. That's why there's a point there. And then it's just the quadratic function x squared plus 9 for all x values to the right. We have our piecewise function. Now, it looks like mine kind of points downward there. Imagine that's a completely horizontal line. That's the line y equals 9 until x is 0. And then it's the quadratic function x squared plus 9 for values of 0 and to the right. So that would look like our function, and they just have you match it with their solutions, and you can see there's only one that comes remotely close to looking like it's supposed to. So of course that's our solution, and that would be section 1.3. I told you it was a short and pretty easy section, but please let me know if you run into any trouble. I want to make sure you get off on the right foot in class. So please let me know if you run into any problems, and I'll be sure to help you out as best I can.